The classic problem that involves the ideal gas law equation and Dalton's law of partial pressure is called collecting a product gas over water. And this is usually done when a reaction produces a gas, that the gas is collected over water, so it's bubbled into a container that contains water and the gas is trapped in the space above the water. What makes this question a little bit difficult is the fact that water evaporates, so it will be producing a partial pressure involved in our calculations, and this is going to be called a vapor pressure. We will talk about vapor pressures more later on in this textbook. The vapor pressure of water is something that we can look up, and so this will be given during this question. So for a gas that's collected over water, the total pressure of what we've collected is going to be equal to the pressure of the gas produced by the reaction plus the vapor pressure of water, and then this is going to be equal to our barometric pressure. So the outside pressure is going to be what's holding the water in place. I give you the following reaction. You can see that we are producing hydrogen gas as part of this reaction. The reactions run and we collect a volume of hydrogen gas over water of 0.5 liters. We know that the temperature of the gas mixture is 26.0 degrees C and that the total pressure of the gas in a flask is 0.980 atm. Really what this question is asking is how many moles of gas are in this flask that we have captured our gas in, and that's going to be equal to the number of moles of hydrogen gas plus the number of moles of water represented by our water vapor. And then the next question is how many moles of hydrogen did we prepare? So we want to know how much of our product hydrogen that we produced. Here the vapor pressure of the water is given, so this is something that we can look up. We know what the vapor pressure of water is at our given reaction temperature of 26.0 degrees C, and that is equal to 0.0332 atm. In the first step of this problem, we are actually going to use a static ideal gas law problem, and in the second part of this problem we're going to utilize Dalton's law of partial pressure. The first thing we want to do is find the total number of moles inside of our reaction flask. So we use the ideal gas law, PV equals nRT. We solve it for N. N, the total moles of gas, is equal to the total pressure times the volume divided by RT. The total pressure was given in the original question. The volume was given in the original question. R is a constant, and the temperature was given in the original question, but we needed to convert degrees C into K. When we're done with this, we get that inside of the reaction flask, the total number of moles of gas is 0.02 moles of gas. But we have to remember, of this mole, some of it is due to hydrogen and some of it is due to water. And so what we want to do is find the partial pressure of H2. We know that the pressure total is equal to the partial pressure due to water, or the vapor pressure, plus the partial pressure of hydrogen. If we solve for the partial pressure of hydrogen, that's equal to the total pressure minus the vapor pressure of water. The total pressure of the reaction flask was given. The vapor pressure of water was also given. When we subtract one from the other, we get that the partial pressure due to hydrogen is 0.94 atm. So we're not quite done. Remember, we're looking for the number of moles of our hydrogen gas. To do this, we are going to use the fact that the partial pressure of hydrogen divided by the total pressure is equal to the mole fraction of hydrogen. The mole fraction of hydrogen is also equal to the number of moles of hydrogen divided by the mole total. So if we get rid of the mole fraction, we can equate this part and this part together. I then solve for the number of moles of hydrogen. That will be equal to the partial pressure of hydrogen times the total number of moles of gas divided by the pressure total. So the partial pressure of hydrogen was calculated right here. Total number of moles of gas was calculated right here, and the pressure total was given. When we're done, we calculate that our reaction produced 0.0193 moles of hydrogen.